Hola a todos. Hoy tenemos a Nancy Elías Rosa, que ella trabaja actualmente en el IEEC en Barcelona. Nancy hizo su doctorado entre Elías y Italia, Padova, y después ha estado de postdoc por el mundo. A ver si me acuerdo muy bien, era como Garching, ha estado en Caltech también ha tenido una beca, una Marie Curie en Italia, una Juan de la Cierva, no me acuerdo muy bien dónde.
La Juan de la Cierva en el IEEC.
En el IEEC, exacto. Y eso, y ahora está de vuelta otra vez en España. Y hoy nos va a hablar sobre Supernova. Así que, cuando quieras.
Gracias. Bueno, la primera parte, gracias por venir, aunque son las 10:30 de la mañana, que mucho sé que es difícil. Y gracias por darme la oportunidad por hablar. I think now. So, like the title say, I am going to speak you today about the interacting supernova and supernova impostors. And I am pretty sure you know what is a supernova. The supernova is the endpoint of the evolution of some stars, and they are one of the most energetic objects in the universe, and they are also more, quite influencing in many aspects events in the universe, because they can be relating with the chemical composition of the galaxy, with the energy, and even with the gravitational wave, which is a hot topic right now. Also, I wanted to show you a little of introduction, because I am not sure who know about supernova, who know. The first plot was this, like here. In 1941, it was the first classification of the supernova, and it was classified depending on the lack or presence of hydrogen. So it was created in the Type 1, the Type 1 or the Type 2. But with the time, the people start to see that there are more features and more diversity between them, and the classification start to split in other subtypes, which it was more or less in 1980, and it became the 1A, the 1BC, the 12B, the type, all this is here. And one of the distinctions here is that when you have this subclass were created depending on the difference in morphological difference in the light curve and in the spectra. If you have the difference in the light curve, you have the letter in, this is a capital letter in the subclass, and if this is in the spectra, you have the small letter in the subclass. So you have also, like you can see here, you have helio or no helio, but all this classification was focused in the early spectra of this object. But it is not always accurate. This is what we use for the classification, but this is not accurate, because with the time the object can change the aspect of the object, and sometimes you can be affected for some aspect of explosion or even for the circumstellar material around. So most of the time usually we classify that for the mechanisms of the explosion. So it is if this is a thermonuclear supernova or this is a core collapse supernova. The two mechanisms. But this is what happened until now, and the diversity now the thermonuclear supernova are a binary system with a 1 white dwarf or 2 white dwarfs, but in the core collapse supernova we have a huge diversity between them, and this depends on the progenitors. Depends on the explosion properties and in the progenitor properties. For example, in the composition, in the CSM, in the temperature, in many aspects can change the shape of a supernova. Here you can see we have different spectra, like I showed you before, with the hydrogen for the Type 2, or if you have helium or the silicon, you have this difference. So it is a really important aspect in the supernova, not only know the supernova, but what we want with the supernova is also know how the stars end the evolution. We want to know how is the properties of these progenitors of core collapse supernovae. And this is a old plot, but really good plot in 2003. And here you can see what's the theory aspect that the supernova, how are the progenitors of the supernova. For example, we have the Type 2P, that this is expect that they explode between 9 solar masses to maybe 40 here, or the Type 2L and 2B is this region here, and obviously the 1BC, because they have not helium, they can't have or not have helium, or they have hydrogen, they are more relating with Wolf-Rayet. But this is what the theory aspect, this is what we have. So, for example, we have the Type 2P, is expect in blue is what we expect, and the plot here is what we have observed. how we observe, a break here is how we observe progenitors. There are several ways. The undirected ways in which you analyze all the observables of the object, or you have the direct way in which you go back, you know how is the position of the supernova, and you go to some archive image and try to pinpoint where the location of this object is there and see if they are one star in the same position. And these are all direct identification of the progenitor of the supernovae. And we expect that the type 2P are from 9, I say before, to maybe 40 solar masses. Instead, we find only from, we have discovered around 15 or 16. We have done, the direct identification of the progenitor of around 15 or 16 core collapse supernovae type 2P. And they all are between 8 but 18. They are nothing up of these 18 solar masses. Instead also the type 2L, type 2N, and type 2B, we expect something bigger. Instead, they are nothing there. We don't detect anything. The type 2B are, some of them are being detected here, and they are more relating with binary system and not with an individual star. And the type 2L, also, there are some attempts, but they are also in that region, always. And the only clear case of type 2N is here, this violet line here. So this is a big 50 or 60 solar masses of a star. And in the case of the 1BC supernova, which should be in that region of Wolf-Rayet stars, we don't find any of them. We have observed at least 16, 17 or something like this, and we obtain only upper limits. So if this object came from Wolf-Rayet star, and this Wolf-Rayet star are big star, we should detect them, but it is not the case. So this is what the theory tell you and what we have observed, but this is going to be more complicated now. Because in the last decade, there have been many wide-field sky surveys that have observed thousands or hundreds of objects. For example, Gaia or Pan-STAR are one of the feeder of that survey. And just to tell you that from 2016 we have classified more than 2,000 supernovas. So this graphic, this plot is even higher. And there are groups in which is dedicated to that. And what that means in our plot before, that means that the traditional classification that I showed you before have been populated in several ways. There are many subclasses of supernovae now because they are weird or they are different for some reason, and we start to create different things. So translating that classification plot in that graphic, in that diagram of phase space, we have here what we know about the nova. Here are the LBV, the luminous blue variables, and here are the core collapse supernova or the Taiwanese supernova. And the rest of the plot has been empty for years and years. But with this new Wi-Fi sky survey, we have populated that. And we are interested on mostly in the unknown part. We are start to fill in that, fill in the bright thing, the superluminous supernovae, and also the faint objects we have been discarding for many years because they were faint. So today, I would like to speak you most about this region here. This region here is intermediate luminous optical transients, and they are several families, but in particular, I want to speak to you about this giant outburst or eruption of very massive stars. But like the title say, I will plot you both things, interacting supernova and this other family of supernovas. So, interacting supernova is characterized, it's a subclass of supernova, is characterized for the blue continuum here. And we have a multi-component Balmer lines. We have narrow lines for this, the subclass is called 2N, for the end of the narrow, which is the material that, we have the supernova here, that the supernova explode and have the ejecta. And this ejecta interact with the circumstellar to the material around. In that interaction is where we have all this line, and the narrow line in the Balmer emission is the material that this is outside. That this is photoionized, but this is not affected by the ejecta yet. They are also, they are luminous, but they are a lot of variety, And because of this interaction, they are also good objects to be observed in radio or in ultraviolet wavelength. About the progenitor, so the progenitor should be something luminous, something with a big mass. This is what we expect, and they are. The favorite scenario is that it's an LVV-like progenitor, a luminous blue variable star, but there are also possibility that they are supergiant or yellow hypergiant or even super HVs. And even there are also people that support the idea that this is a binary system, interaction in a binary system. The only clear object is the one that I showed you before, and this is an LVV. So just to make a break, an LVV is this is blue, is luminous, and is variable. This is exactly the definition. And we can have giant eruptions, or we can have oscillation, eruption. There are many variability in this stage of the star when this evolve. The most famous LVV is Eta Car. It is in the Milky Way, like you can see here. Has been really. So I show you what is the supernova impostor, what is the part of the interacting supernova, but now we have what is an impostor. This is a new and rare family of events that we have been discovering more and more in the last few years. And the fact that this is called supernova impostor is because that mimic the behavior of a type 2N, the behavior of the interacting supernova. This was the first time that one in supernova impostor was identified and was labeled with the word supernova impostor. It was in 2000, and all that started when we start to have enough image from HST in which we come back to the field to see if the object was there or not. And the progenitor in that case, the star was something between 60 solar masses. So, like I said before, why is called impostor, supernova impostor? Because they are not supernova, they mimic the behavior of the spectra. They are blue continuum, and they have dominating by the hydrogen line. Here you have the clear example that I showed you before, 2005 GL, and here you have a spectrum quite blue with the narrow line of the hydrogen. And here you have a family of LVVs or impostors or supernova in which all the spectra are the same. You have the blue continuum and the hydrogen. For this reason, most of the time we can confuse in the classification. But one of the differences is these objects are quite faint for supernova, and they are quite erratic. This is a plot of many impostors put together, and all of them are below 14 or 15 magnitude, in absolute magnitude. Instead, if you come here again, this is the same. Here is a compilation of objects, and in between them is also the object that I showed you before. All the supernova, interacting supernova, are much brighter than this magnitude. But the main difference between this object is that for a supernova impostor, the star survives. This is, instead of supernova, the star is destroyed. I mean, here in that plot, we have again to the same case as before. We have three plots. Here is when the supernova exploded, 2005 GL. This an image was taken from HST before, and this was taken in 2007, 7 years after. And like the black circle, the white circle here is signed also in the other image, and you can say that it was something here in 1997, but it was nothing in 2007. So the star disappeared. So this is the progenitor, and this star was a kind of a massive blue star of more than 50 solar masses. Instead, in the case of the impostors, this is just material that is erupted, is an outburst, but the star is still there. So as much as we have been observing this object, it has been just a couple of years ago, as much as we observe as wide is the diversity between them. But now we are in the position that we can start to, the new challenge now is start to study the families, because we have had maybe 4 or 5 objects, but now we can put them in similar characteristics. Obviously, I mean, this is 4 families that I will show you now, because this is the topic of the talk. And we have objects in which we have this big eruption, or we have a very slow evolution, object that we have several, or even that we never have this big peak here. It is, I need to confess that for each of this family, maybe we have 3 or 4 objects. We don't have much of that, so the statistic is not that big, but this is a starting. This is a new challenge. So the big eruption is objects like this. You have all these, how we work here. When you have the eruption and you discover this object, for example, here, in that position, you come back to all archive image possible that we can put our hands on. And we try to check if was something there. So you can see here we have some upper limit, so nothing was brighter than that. In that case, it's another case, it was some history. And the peak, we have suddenly a big peak, and the object really quite decay after the peak. But in any case, never it is brighter of -15 magnitude. In that case, the progenitor, we went to the HST image, and the progenitor was a massive star, not that massive as the others. And but this is upper the limit of the type 2 peak. The other object is this one, UGC 2773 OT. And here you can see it is this blue light curve here, which we have a rise of 5 GRs. This is a really slow evolution. The spectra are like we saw before. This is practically blue and the Balmer lines. And in this case also is a massive, the progenitor could be probably a massive star. This object compete with Eta Car, which is here. And Eta Car have also a really slow evolution. But the difference, for example, is that you have here peaks in Eta Car because the movement of the binary system. Instead, for that object, we have not this peak. Also, the particular thing in that case is that in the spectra, if we do assuming in the in the hydrogen lines, we can see they have this profile here. This remember a lot the homolus, the material that this is around the Eta Car. The third family is with a lot of outbursts, like I said before. Here we have this object that you have at least 2 or 3 outbursts here. The spectra are always the same, but in that case, this is more. It's called now more a luminous red nova because it emits mainly in the red part of the diagram, but the magnitudes are comparable most with the nova. Also, in that case, it's a big star, probably a massive star, which is the progenitor. And the last group that I showed you in that part is this. This is 2000 CH. And here you can see we have this recurrent outburst. We have a lot. We have been following that first in 2000 and later from 2008 until now. Even now we are still doing that. And you can see how it is moving. In some moment probably we will have this big eruption. And we are expecting for that. So this is the plot that I showed you now. I mean, I show you what we have right now in that field. We have supernova interacting, and we have the supernova impostor, which mimic the supernova interacting supernova. And we are starting, like I said before, to distinguish them, to put them in families. At least now we know what we want. If we saw some object that is faint, we don't discard that we did before, and we observe and follow that, and we have material from another telescope. But sometimes that line between supernova impostor and interacting supernova is not clear, this division between them. So, for example, this is the first object in this category. It was it has been taken. The authors of this work have been fishing again and again this object because to see if this is a supernova or a supernova impostor. We have, like I said before, you have Balmer line, and you have a magnitude that this is faint to be for a supernova, at least for the first epoch. But it is still in debate because there are people that say that this is a core collapse supernova. Instead, there are people that say it's an impostor. Many of the reason is because the dust. There are people that say that there are a lot of dust around, and for this reason, this is the disappearance of the object. Some people say no, but this is just a historic object because I want to show you what was the first one. But the smoking gun of this family, in which we don't know if they are supernova impostor. We don't know if the supernova impostor label is just a preliminary evolution of the star, the last evolution of the star that start to have that variability to later explode like supernova. We don't know if they herald the supernova explosion. But it was the smoking, and from here, from 2009 is when we start to do all this campaign of observations. This is a pretty nice object. This was discovered in 2009, like the name indicates, and it was faint. Minus 14, like I said before. It was probably an eruption. After a while, the people thought it was a supernova, faint supernova. We put aside. But our group go on with observation. We know with observation of this object. And in some moment, we have all this oscillation. We detected this oscillation in 2011. And finally, in 2012, we have two bumps, two peaks. They are zooming up here, zoom up here. You have an event A and an event B. There are many theories, and I will come back to that in the couple of next slides. There are theories of what that means. But I will tell you first that, okay, the progenitor, I will come back, okay? So, sorry. What I can say is this was the first one, but we know now what we have. So we start to look with more attention to other objects, and we have collect 5 of them at the moment. All of them, it is a family, like say, and we have all this evolution before the big eruption or the supernova explosion or the collision or whatever it is here. Sometimes we have upper limit, sometimes we have detection. 2015 B8 was a nice case because that bump here is because it exploded in a factory of supernova in a galaxy with other supernovae, which we were observing many years ago. So we could revise this image and put all these points here. And the particular thing is all these events have this erratic thing. They have an event A and a second event B. And more interesting is that while this event is a little heterogeneous for all of them, the interesting thing is the event B is the same for all of them. So it's, and after, I didn't plot here, but after that, the typical light curve of the supernova, I mean, you decay here and you have a flutter for the decay of the cobalt to the nickel. So in the spectral point of view, we have all of them the same at the early time. We have the blue continuum and the Balmer lines. In the after maximum, we start to have pitch union in the hydrogen line, in the hydrogen emission, which is more typical for other subtype supernovae, but this is typical for supernovae. And in the last time, we have asymmetric Balmer line, but this is also normal because you have the circumstellar material around. You start to be affected for that, and the circumstellar material could be different from star to star. But this object, 2009 IP, was estimated that it was a very massive star from HST image with masses of between 15 and 80 solar masses. And it is not plotted here, but in the paper was compared that object with the interacting supernova that I have been showing you for all these slides. And the spectra at the early epochs are quite similar. So if these two objects became from the explosion of progenitor, of very massive progenitor of more than 50 solar masses, we assume that this family also have progenitor of that magnitude. But are they supernovae or are they core collapse? They are supernova, they are impostors. That is the question here. So for the energy, for the velocity, for the lack of outbursts after the main peak, we can say this is a supernova. But the nickel, the mass of nickel, which is one of the motor of the explosion, is really low, which is not typical for a supernova, but not impossible because could have other mechanisms behind. And they are not they are not line of the nucleosynthesis in the spectrum. Maybe here a weak oxygen, but who say if this is noise? I mean, it's quite difficult for people to say that this is oxygen and not noise here. And the interpretation of these two bumps that we've saw before, there are plenty of papers that have coming up from 2009 IP. There are people that think that the two events are because in the first one you have a collision, you have an outburst, and in the second one, the big one, is a collision of shells. who is creating you this peak, generating you this peak. There are people that say instead that the first one was a weak supernova, and the second one is the interaction of the ejecta with the CSM. There are people that say the contrary. The people say at the beginning was just an eruption, and the second one we have the supernova, the actual supernova. Or even in the last years, there are people that suggest that this is a binary system, and in the first one we have the interaction between the two stars, and the big peak is due to the merger of these two stars. So there are plenty of options, and we understand very few about that at the moment right now. Another object I wanted, because it's my talk, let's say, and I wanted to show you this object that I have been studying also, and it's not that easy. I mean, not all the objects follow this family of 2000 IIP. In this case, I started to study this object because I thought it was a Type In, and it was nice. It was I have image in HST, so when I was interested in the hunting of the progenitor star. But when I compare the object is this green line here, and this is not, yeah, it's similar to the Type In, but it's more similar to the violet star here, which is 2000 IIP that I showed you before. The only difference, or the main difference here is, for example, that this is the thing that Shane or may you have doubts about, because the magnitude is higher than what you expect. The spectra are similar to 2000 IIP, and the other core collapse, and in the end, we have a weak spectra, because as you can see, one of the particularity thing of this object is that we lose the object after the maximum. We have the maximum line. In this gap here, it was behind the sun, so we couldn't observe this object, and when we take the observation again, the object was not more visible, which is not normal for a core collapse to interact with supernova. We have just this point here, which is from HST. But why I put this object here is because this is similar to 2000 IIP, and HST gives us a lot of information. When I went to HST forget about that because it's in the U-band, so you cannot see very well the image here, but see this plot here. This is when an image of the HST when the supernova was there. You have here the position of the supernova and just three squares just to guide you in the image. Supernova is here. When I went to the archive of HST, I discovered an image in 1994, and the object, something was at the same exactly position of this object. I think when I study this object, this has a magnitude that this is not the magnitude of a normal star. This seems the magnitude of outburst in a star. This is more minus 12, minus 13, which is more not for a progenitor in quiescence, but this is more of a progenitor in outburst. For example, for 2000 IIP of the other object that I showed you before, the magnitude was minus 10. Instead, here is minus 12. So this was something in action when we took the image here. But when we came back to the object in 2015, the object was no more there. No more there. So here, yes, the theory, I mean, I put the paper that I am more in the position that it was a supernova, and we have no more supernova, and we have here the proof that it was something before. It was a big object that was in eruption. It was in variability before. But obviously the data were not, I mean, I have not enough data to say that is for 100% that. There are always doubts, because you can also tell me that here maybe there are dust, and for this reason I am not seeing what is behind. It could be. But I am more for that this is a supernova. And another kind of object that I have been studying on this that you don't know if this is a supernova, this is an impostor, is this. This is the last object. This is supernova hunt. Okay. The name of supernova is, we can have a completely talk about the names of supernova in another moment. So it has been a mess for years, and when the Whitefield Sky survey came up, each survey wanted his name in the name of the supernova, so it became a crazy thing. But in a couple of years, we have we are in agreement, and we put all with the same name right now. AT and the year, and later the letters. AT is because it could be a transient, just a transient. When this is classified like a supernova, we change AT for SN, like a supernova. If it is an impostor, it's a stay for AT. AT, sorry. So this object here was for survey called GIANT, and it was 151. And it is also, we have some history before, okay, upper limit, but we have some history, and then suddenly we have this big peak here with event A and event B. The thing is, this event A is 450 days, so this is too slow in comparison with the object that I showed you before. And the peak B also, this is too large, too broad also in that case. So like I say, when we start to see things, similar things together, appear this guy and say, all is different. We have exception again. The spectra they are nothing, not evolution at all for months. This is questionable because the one is from the spectra and one for the photometry. So the temperature evolution typical of the supernova is not clear that they are evolution. Also the velocity of the line are not evolution. We are sure that we have a multi-component object with a multi-component emission line of nitrogen, which is here. So in that case, we can say that this is similar to 2009 IP, like I say, because for many reasons it is similar to that family, but we have no significant variability before, brighter than this magnitude. We have an event A which is different and an event B this is completely different than the other. So here we have another incognito. We don't know what this object is. The best hypothesis here is what we are watching, what we are observing is just a nebula, a cocon of material, and inside we can have whatever you want. I mean, we can have supernovae, we can have stars, we can have, we have a merger. So just for fun, I put together all these points. I went to the literature, I went to each one of these objects, and I put them here in equations when they are not with variability and when they have invariability. Here in that yellow area here is when they are in outbursts, all fall in that area. But like you can see, it is a mess. I mean, they are not, they are objects that we are not clear. We have not an answer of what is a progenitor. The only answer is the progenitor seems to be a big massive star, and we are favored for the LBB-like stars with masses bigger than 50 solar masses. This is the only hypothesis that we can hear. But one of my ideas is also try to do this work in a systematical way, because here I just went for each paper and pick up the numbers, and each author have a different way to measure these things. Or even come back to the field and see if the object is there or not. But this is future. So what I want that you remember from this talk is just that we don't have supernova alone. We have also other things. We are family, for example, called supernova impostors. They are in common. They have in common that they have the blue continuum and they have the Balmer line. For this reason, we confuse them. We have some uncertainty at the beginning, and they came. We are favored on that to the scenario that they came from a very massive stars, and they are wide diversity. But the difference between them is, in the impostor case, we don't have a terminal core collapse. Probably we don't have a nickel powered tail, and we don't see the nucleosynthesis ejecta. This is the main difference. But more interesting is that maybe this supernova impostor can be the beginning of this supernova explosion. But the theory don't share that idea. I have been reading papers of modeling, and not all authors are not everybody thinks that massive star of 30 solar masses can explode that supernova. So my concerns are exactly that. What produced these outbursts? I mean, it's possible that massive stars of more than 30 solar masses can explode like supernovae. When and why that happened? Why not in all the cases? Or if we come back, if we say that a massive star explode like supernovae between 8 and 19, why we don't see nothing bigger than 18 solar masses? There are still a lot of incognito here and a lot of work here, but okay, the challenge is to go for that. And mainly now, this is future because we are involved in these two consortiums. This is LSST, and LSST is coming with thousands of objects right now. No, in the future when LSST starts, we this telescope is going to observe thousands of objects a day. So in that moment, we are start to moving, to prepare, to create catalogs, to create templates, to see if we are able to handle that. But I think it's going to be food for everybody, because I mean, there are thousands of objects. And also, this is SOX. This is an instrument that is going, I think is already approved. It's going to go to NTT instead of IFOS DUE. It's in IFOS 2, sorry. And this is like son of IC shooter. So this is a small version of the IC shooter. It's going to observe simultaneously optical and near infrared, not the ultraviolet. And it's going to be dedicated mostly for these transients that we don't know, that these new families of objects that are coming up. So and with that, thank you to everybody for coming.
Thank you, Nancy. Is there any question?
Thank you, Nancy. I have a comment and a question.
Yeah.
The comment is that it reminded me the situation with biology, for example, in the 50s, and there is a famous quote by, I don't remember who, a biologist telling that we had a lot of wonderful data, but it lacked the intellectual lazo that tied together. I mean, you are discovering, don't worry, you are now in the phase of discovering many subtypes,
Yeah.
many classes, and this is, I mean, it's necessary too. And the question is, what is the percentage, because you are talking about core collapse supernova with massive stars, beyond, I don't know, 9 or 10 solar
Yeah.
masses. How many of those solar, massive stars are in our galaxy? Is there a census? Is there a monitoring of them? Because there should not be very, very many of those.
Okay, for this massive star, I know recently appeared a paper about the study of LBVs. I don't know the percentage. I know there are works on that. I don't remember honestly. I can give you the
Maybe
reference.
thousands.
LBVs.
In total, I mean, stars supposed to finish with supernova, say beyond 10 solar masses. Up
For
to
example,
100.
I know from Wolf-Rayet there are 12% of stars are Wolf-Rayet in our galaxy. That study has been done. This is one of the reasons because we say if the theory say that a supernova that have not hydrogen, have not helium, came from the Wolf-Rayet, and this Wolf-Rayet we have 12% in our galaxy, why we don't see them? This is one of the reasons. That for sure I know the number. LBVs, I'm not sure. I know it was recently a paper because with now Gaia, the people make an observation, but there are thousands of them. We have a project, I am involved in a project in Padova in which we have picked up all, no, we don't have thousands. Honestly, I think the list is smaller, but more than 50 for sure we have that we are continually following. I mean, maybe once each 2 weeks or something like this, we go and take at least one image in R band to see if we detect something in R band, we open all the available telescope. But the quantity of stars is big. It's bigger now. Also, we have always thought that the progenitors of the supernovae came from a single star. Instead, in the universe, it's completely demonstrated that we have more binary systems than not single star. Oh, we have plenty of them. So now the people start to think that most of these stars, maybe for the distance, we see that this is a single object, but actually this is a system. But we are in work program. I mean, slowly, like I say, we have the idea. This object has been ignored for years because they were faint, and we have not also the capability in the telescope because the telescope were not able to observe something so faint, the small of 1 meter or 2 meters. Now we have telescope around the world. We are a huge community, and when you don't have time, you contact to someone and can observe you something. For example, we have a program in GTC in which we have this to observe late spectra of this object, or when we really need high precision to identify the lines. So now the things are going on, so I hope our intellect is going to improve that and give some clue. But the thing is, we have that, and we say, we have that, can you tell me, the theory people can tell me, what is this? and they are not questioned because the theory were thinking in a way, and now we arrive with that. Because I check, and there are no theory that the star with mass bigger than 30 solar masses can explode. But I have here.
Yeah, this was my other comment is most of them should be binaries. So keep an eye to the theories that are working now in the evolution of binary systems related to planetary nebulae, for example, which is now a very active field of research, including the common envelope evolution at the latest stage. I know that this will be difficult. And it will include another degree of freedom in the system,
Yeah, exactly.
which is horrible, but yeah.
It is one of the thoughts that this object, for example, came from that instead we have seen a binary system in a common envelope, and in some moment they merge. But in my personal case, I have been checking papers, and I don't know if this is possible in that scale of time. I don't know if a merger could happen in months. Honestly, I don't know, and I don't find the references of that. But this is true that now we are more focused. We have more in the head the idea of that as a binary system, but this is going to be a really huge challenge to identify that.
Thanks for the nice talk. So I have two questions. Maybe they're silly. I don't work on supernovae.
They are never silly
okay.
questions.
Well, they could be silly, right? You can tell me. So the first one is, how do you determine the progenitor mass of a supernova? And how well can you determine the progenitor mass?
Well, I mean, I start from the beginning. Well is a questionable also reason. So what we do with the hunting of supernovae is we have the supernova what we used to do is that we have the supernova and we at the position, and we try to point, to be as much accurate as possible of the supernova position, and we try to look for a big telescope in the archive that have good image. HST has been the salvation for many years, and with that position we try to identify something there. And with that, obviously, if we are lucky and we have a color, we can go to our diagram and we can put there with evolutionary tracks. If we are not lucky, which used to happen, what we have is the line that you see here. I didn't tell you before, but these lines is because I have not color. I just have magnitude, but I have not color. I don't know if, for example, the progenitor of 2000 IIP is if color is hot. I don't know the star. I just know that's the magnitude. Yes, there are uncertainty, a lot. We try to be as much accurate as possible. Also, there are uncertainty in the absorption, in the metallicity. Because if we are lucky and this galaxy have been observed for metallicity proportions, or we have a map of the metallicity, we are able, most of the time you need to assume. If the galaxy have this metallicity, maybe the supernova have that, or something. There are a lot of uncertainty, yes. But, for example, we can have a certainty, but we are in the same, like I say, I cannot be precise, but I know it's in this region, when I say, maybe I cannot be precise what is the mass of an impostor or interacting supernova, but it's not in that below part of diagram, it's in the top. So maybe I cannot tell you this is 55 solar masses plus minus that error. No, for this reason, most of the time we give a range of masses because we have the uncertainty.
Thanks. And so the other question was, so if you mix up a supernova for a supernova impostor, and you measure a distance, can you measure a distance from the outburst of a supernova impostor light curve? I mean, if you were
the light curve,
if you were to confuse them, right?
Yeah.
So you're observing a supernova impostor. You think you're observing a supernova.
For many years before, we have been confusing supernova impostors and supernova. Now, when we see something that this is so faint with that characteristic,
you now know.
The alert start to ring and say,
I see.
It could be no.
Okay, all right.
How determine the distance? You need to go to the host galaxy because we don't have many options. Or if you are lucky and maybe you have sometimes you have lines from the galaxy or from some H2 regions, and you can see this narrow line, and we can try to
Sure. But, I guess I was thinking of things like, you know, the expansion of the acceleration, the expansion of the universe was based on supernova observations. Could
with
some
that guy,
fraction?
no, because
Right.
we don't have it. We don't know how is the behavior.
Yeah.
So we have done the expansion of the universe with the Type Ia supernova, which has been commonly think that they are homogeneous, which is not quite true.
Mm-hmm.
And right now also the people is pointing to the Type 2P. They have been trying that with the spectra, not with the photometry, because the lines of, I think it's iron, where they measure to, I don't remember exactly why, honestly. And now in the last years is with this new family, which is super luminous supernovae, which is in the top. They are magnitudes of minus 23 or 24. They are, and they used to have a really high redshift. So with that, there are groups that are trying to study. The problem is, at the moment, we don't know what is the what create that extra energy in the supernova. There are people that think it's a magnet star. There are people that say it's just collision. There are still discussion because we are putting models and whatever model fit. I have one report on that, and I have the 3 models, and all of 3 fit. I say, what I can say now. But there are groups dedicated to, they think that we can measure because they are more homogeneous, and they can measure the expansion. But for this guy, I honestly don't think, in that moment for sure no. I mean, I don't know what is going to happen. If we will be able to create families of 1,000 or 100, maybe we will be able. If we found something. For example, yeah, we don't know honestly.
Any other question? I have one myself. So for this type 2 PL, where you don't find progenitors with more than 18 solar masses, does it mean that they directly form black holes in the dark, or do you know?
No.
idea.
I mean, one of the theory, no. I mean, there are theories. This is one of things that I would like in some time of my life, if I can study. There are theories in which they say, for example, the opposite of a supernova. You have the dark supernova. It means if you have a star and suddenly you came back again and you don't have more than the star. Because they have the star, when arrives to the end of the life, the evolution have not enough energy to expel all the material. Instead of that, came inside of the nuclear and create a black hole, and you, instead to have explosion, you have all the things inside, and the supernova disappear. This is called dark supernova. This is one of the theory of what happened with stars of more massive stars. But honestly, nobody knows. The fact is that the theory said that we can find out, I mean, that the fact is that in 15 or 16 Type 2P supernova, Type 2P are more common that you have the hydrogen, and more common to find. And in any of them, we have find anything more massive of 18 solar masses. What happened? I say they are always theory for everything.
Well, if there are no more questions, we thank the speaker again.
Yes.
And just remind you that there is scientific coffee in the cafeteria, and you are all invited.